name of Almighty God, I'm Master Sankoshi, and today I want to talk about chemical reaction engineering module in COMSOL multiphysics simulation software. The functionality of for simulating fluid flow in free porous media is found under the fluid flow branch when adding a physics interface. The documentation of the variable interfaces and features can be found in the CFD module user's guide in the chapters single phase flow interfaces and porous media and subsurface flow interfaces. Modeling fluid flow. In this section, we want to go through the available physics interfaces. The next one is coupling to other physics interfaces. The first type available physics interfaces, this module primarily models the transfer and conversion of mass in chemical reactors and other reacting systems. Many of these applications include transport through convective, and the module includes a number of physics interfaces for the simulation of fluid flow, particularly within porous media, as with all other physical descriptions simulated by COMSOL multiphysics. Any description of fluid flow can be directly couped to any other physical process. This is particularly relevant for the systems based on turbulent or multiphase flow, which are supported by the safety module. For detailed descriptions of the fluid flow interfaces listed below, see the CFD module user's guide. The fluid flow branch has a number of sub-branches to describe momentum transport. The laminar flow interface found under the single-phase flow branch when adding a physics interface is used to model laminar flow described by the Navier-Stokes equations. It is also possible to extend this physics interface to study non-thermal or non-Newtonian flow. The cryptic flow interface, also under the single-phase flow branch, is used to model flows at a very low Reynolds number, also referred to as a Stokes flow. This typically occurs in fluid systems with high viscosity or small geometrical length scales, for example, in microfluidics and MEMS devices. The rest of the available physics interfaces for fluid flow are found under the porous media and the subsurface flow branch. The Darcy Law interface is used to model fluid movement through intersections in a porous media where a homogenization of the porous and fluid media into a single medium is done. This physics interface combines the continuity equation and an equation of states for the pore fluid or gas, can be used to model low velocity flows for which the pressure gradient is a major driving force. Darcy's law can be used in porous media where the fluid is mostly influenced by the frictional resistance between the pores. When the size of the intersects are larger and the fluid is influenced by itself, the kinetic potential from the fluid velocity, pressure, and the gravity must be also be considered. The Brinkman equation interface is the appropriate physics interface to use. The Brinkman equations extends Darcy's law to describe the dissipation of the kinetic energy by viscous shear, similar to Navier-Stokes equation. Consequently, they are well suited to transitions between slow flow in porous media governed by the Darcy's law and fast flowing channels described by Navier-Stokes equations. The equations and boundary conditions that describe these types of phenomena are also found in the free and porous media flow. Brinkman equations. The free and porous media flow Darcy interface models porous media flow connected to free flow domains. This multiphysics interface coupled the laminar flow interface with the Darcy's law interface over their common boundaries. The next section briefly discusses coupling to the other physics interfaces. Now I want to go through the coupling to other physics interfaces. Often you are simulating applications that couple fluid flow in free porous media to another type of phenomena described in another physics interface. This can include chemical reactions and mass transport as covered in the chemical species transport branch, or energy transport in the porous media found in the heat transfer branch. More advanced descriptions of fluid flow, such as turbulent and multiphase flow, can be found in the safety module. More extensive descriptions of heat transfer, such as that in turbulent flow or system including radiation, can be found in the heat transfer module. Furthermore, some applications that involve electrochemical reactions and porous electrodes, particularly in the electrochemical power source applications, are better handled by the battery design module. I want to go through the heat transfer interfaces chapter. The functionality for simulating heat transfer in free and porous media is found under the heat transfer branch. When adding a physics interface, the documentation of all features in heat transfer in porous media interface can be found in heat transfer module users guide in the chapter of heat transfer interfaces. Now I want to go through the modeling heat transfer, available physics interfaces. Heat transfer is an important part of chemical reaction engineering. Most chemical reactions either require or produce heat, which in turn affects both the reaction themselves and other physical processes connected to the system. The heat transfer branch includes a number of physics interfaces for the simulation of heat transfer, particularly in porous media. As with all other physical description simulated by COMSOL multiphysics and description of heat transfer can be directly cooked to any other physical processes. This is particularly important for systems based on chemical reactions and mass transfer along with fluid flow. You can manipulate these physics interfaces with respect to including source and sink terms, or in other words, account for exothermic and or endothermic chemical reaction. If you are using, for example, you also have the heat transfer module, there are additional heat transfer interface features such as radiation available. Now I want to go to the coupling heat transfer with other physics interfaces. The reaction engineering interface includes support for setting up and simulating chemical reactions, including reaction kinetics through the temperature dependent Arrhenius expression and mass reaction law. This physics interface also has support for including and calculating thermodynamic data as temperature dependent expressions. The reaction engineering interface can generate a space dependent model using any heat transfer interface to benefit from the bidirectional dependence between heat transfer and chemical reactions. More advanced descriptions of fluid flow, such as turbulent and multiphase flow, require the safety module. In addition, the heat transfer module also includes more detailed descriptions and tools for simulating energy transport, such as radiation. Now I want to go through the thermodynamics. This chapter describes how you can use thermodynamics functionality to define thermophysical and transport physical properties. The properties in turn can be used when simulating chemical reaction systems or any type of transport model involving mass transfer, fluid flow, or heat transfer. In this chapter, we want to go through using thermodynamic properties and also thermodynamic models and theories. Now I want to go through the using thermodynamic properties. In this section, we want to go through the workflow for thermodynamic properties calculation, thermodynamic system, external thermodynamic package, external thermodynamic system, predefined system, exporting and importing thermodynamic systems, species property, mixture property, equilibrium calculation, generic chemistry, generic material, coupling with the reaction engineering and the chemistry interfaces, evaluating a property function in a physics interface, user-defined species references. Now I want to go through the workflow for thermodynamics property calculations. The thermodynamic properties database together with the thermodynamic calculator make it possible to evaluate physical properties of fluids such as heat capacity, thermal conductivity, density, diffusivity, as well as equilibrium compositions of two phases at equilibrium. The properties can be calculated for pure fluids mixture and for two-phase fluid systems consisting of pure species as well as mixture. Using the thermodynamics functionality involves the following main steps. Step 1, add the thermodynamics node and create a thermodynamic system to add properties for a selected set of chemical compounds referred to as chemical species in this manual. A thermodynamic system can be created in the following ways. A built-in thermodynamic system uses the built-in or user-defined property database with the native functionality for thermodynamic property calculations. An external thermodynamic system uses properties for an installed external package provider. For more information on how to enable the use of external packages, see the installing external thermodynamic package. An example, a predefined system uses the built-in database with native functionality to set up one of the following common systems: dry air, moist air, or water steam. Step 2, once the thermodynamic system is set up, it can be used to define a multiple of property functions to generate a material option provides a fast route to defining the material properties most commonly requires for fluid flow, heat transfer and mass transfer modeling. By specifying the composition and phase of the mixture, a material node can automatically be set up. The material node can include properties such as density, heat capacity ratio, thermal conductivity, and viscosity. The next one is users of reaction engineering or chemistry interfaces can cope chemical species in these interfaces with the chemical species in the thermodynamic system. When coupling with the reaction engineering and chemistry interfaces, the required property parameters and functions are automatically added and visualized as nodes under the corresponding thermodynamic system node. Step 4. As an alternative to the functions automatically set up when using direct material coupling to, for example, chemistry functions or constants, can be set up manually for any thermodynamic system. This is accomplished using the thermodynamic features, species property, mixture property, or equilibrium calculation. You can, for example, create a species property function describing the density of a fluid and use this function in a fluid-fluid interface. With mixture property, you can define mixture functions, that is, functions that depend on the composition of mixture, describing, for example, density, enthalpy, or heat capacity. The functionalities described in step 2-4 generate functions and constants defined by a thermodynamic system that can be used in any physics interface. In COMSOL multiphysics, the functions are used to evaluate fluid properties that depend on the variables such as temperature, pressure, and mixture composition. For more information, see evaluating a property function in a physics interface. So thank you so much for watching my tutorial video until the end. Today is 14. Today is the 20th of the May 2026. Time is 12:14 p.m. Also, you can download the proper and appropriate and related console multiphysics simulation file from my github.com/masterscript.